Central mass in your book is defined like this: the point at which all the mass of a body can be considered to be concentrated is called center of mass. Remember, in the last title of the first chapter, we said that, or your book said that, Earth is a huge object, and when we are calculating the force acting on a man's body on the surface of the Earth, we assume that the whole mass of the Earth is concentrated at the center in here. So this is the central mass of the Earth. So we assume that all this mass is considered to be concentrated just at one point. That point is the center of mass of the Earth. So this is not only for Earth, for every type of the object, every kind of the object, we can determine the center of mass. Central mass can be found by two ways. One of them, you can support an object from its central mass. Then, if object stays in equilibrium, yeah, that point is the central mass. I want to find the central mass of this ruler. I will start supporting it from different points. When it stays in equilibrium, when I balance it, right here, I balance this ruler from a point in here. So this point is the center of mass of this ruler, which is between 16 and 17 centimeters, right in the middle. 16.5 is the center of mass. 16.5 centimeter, this point right here is the center of mass of this ruler. This is one way. So when you support an object from its central mass, this object will stay in balance, or object will stay in equilibrium. You can find the central mass any object by this method. For example, this is the range. I don't know where the central mass is. You are going to try it right here. So then I supported it. So central mass is right here, just in my finger, in here. And you can try many different types of different shape of the object, and you can find where the central mass is. So I have here in my room thermometer, for example. Where is the central mass? I can find it. So in here, central mass. So this is the one way you can find a central mass by supporting the object with something, or you can suspend by a string as well. So if this object is able to stay in equilibrium, so then you can say that yes, this point is the central mass of this object. And this is the one way. There's other method. There's one more method to find the center of mass. If you throw an object up in air, the object rotates around its center of mass. This is a second way. Then in your book example, given example is that throwing a hammer into the air, but I found a video about not a hammer. When you throw a hammer in air, you are going to see that hammer exhibits two types of motion. One of them is its central mass. Translational motion, the central mass of the hammer follows a parabolic path. You will see now them in this video one by one. Second one is the hammer itself rotates, spins about its central mass, and rotational motion about its center of mass. In the first one, hammer central mass follows parabolic path. Translational motion. Remember, if you study the motion of central mass, so that motion is named as translational motion. And second one is hammer is spinning around in air around its central mass, so it's rotational motion. Let's see, this man is doing an experiment about that. Now he's going to define the motion of this rocket by first one, how one end of this rocket is making motion in air. This is not what we are dealing with, but the second one is not now. Follow central mass motion. how central mass is following what kind of path. It's just a parabolic path, just as if you throw a piece of. But now about central mass, what's happening? So each end of the rocket or hammer, it can be also, so spinning about, circular motion, making circles around the central mass. Let's see once again. This is, especially second and third one is, not this one, but second and third paths are important. Not this one. This is not talk in our book, but incoming one, which is the motion of central mass. Motion of central mass. Focus on the central mass. So central mass and any object, if you throw in air, all they follow parabolic path. Translational motion. Now, rotational motion. End of the rocket or hammer spins, moves on a circular path around the central mass. Okay, these types of questions are can be asked in ministry exam. They can ask you. So if you throw a hammer in air, so the center of mass, this is this statement, center of mass moves along a path of a projectile, all follows a parabolic path. Second one, ends of the hammer will trace out circles around the center of mass. So these two are important examples. For regularly shaped object, generally it's easy to determine the central mass because their geometric center is the center of the mass. For example, for a ruler, remember I just showed you the ruler, it was in the middle, right here. For regularly shaped object, it's the middle. For cylinder, it is in the middle. You can find very easily. Or for a circle or for a disc, again, geometric center. For a square or for a rectangle, again, geometric center in here. So we can get it. But if the shape is irregular, not regularly shaped, like a baseball bat, so one side is thicker, you see, other one is thinner. So in this case, this is not a regularly shaped object. So then central mass will be closer to the heavier part. This is the greater mass, greater. So central mass will be closer to the part which is greater mass. And center of gravity. Center of gravity and center of mass, in fact, same point on the Earth, but their definitions are different. Center of gravity is defined if an object is positioned inside gravitational field of a space body. This definition is not given in your book, but I want you to understand the difference between why do we need center of gravity. Even for most situations, center of mass and center of gravity are the same point. They are same point, but their definitions are different. Center of gravity is defined if you put an object inside a gravitational field of a space body. Yani Earth has a gravity?
Yes,
yeah, in this case, we can talk about center of gravity of an object on the Earth. But you went to the space, a place, empty space, there is no gravitational field. So can you talk about center of gravity?
No.
No, you cannot. You can only talk about center of gravity when an object is inside a gravitational field of a planet or of a moon or of a star. So if it is inside a gravitational field, so. But center of gravity on the Earth and central mass of an object on the Earth are equivalent, same point. Where is the central mass? So that point is also center of gravity. Center of gravity is defined as, in the book, this is definition, is the position at which gravitational force acts on object. Do you remember we draw FG? For example, this is a ruler. So where is the central mass? It is here, midpoint. Yes. So this ruler has some weight. Say that Fg for this ruler is 5 Newton. So from where you are going to draw this Fg? From center of gravity. But center of gravity and center of mass are the same, yes. From this point, you are going to draw the Fg. Center of gravity. But it is equivalent to center of mass. Yes, it is equivalent to center of mass, ama we don't say that we are going to draw the gravitational force from center of mass. We don't say this. We say that gravitational force always drawn from center of gravity. But center of gravity and center of mass are equivalent points. Yes, they are equivalent points.
Teacher?
Yeah.
For space, we said we don't have center of gravity, but do we have center of mass?
Yes, of course, center of mass always exists. It's about the object. It's not about the gravity or something. Just object as a mass or not. Yeah, it is a mass. It's a mass. Yeah. So for every object, whenever you take the object, so object will always have the same point as center of mass. You said center of gravity or center of mass?
Center of mass.
Center of mass always exists, but center of gravity can be talked only if you put an object inside a gravitational field.
Okay, thank you.
If a gravitational force acts on an object, we talk about center of gravity. Equilibrium. Translational equilibrium, you studied in the 11th grade, but maybe you didn't give it a name, translational, but only equilibrium is. Now, translational equilibrium, if the net force acting on a stationary object is 0 or non-zero. Let's start with non-zero. If the net force acting on a stationary object is non-zero, motion with an acceleration will start. Non-zero force means there is some force. It is not equal to 0. In this case, object will accelerate. Sum of the force acting on the object is going to be mass times acceleration, and you can calculate acceleration of the object by Newton's second law. And you did this. We also did in chapter 1, section 3, that centripetal force was a net force or resultant force acting on an object which is on a circular path. What if the net force acting on the object is 0? In this case, object does not start moving. So if net force acting on the object is equal to 0, our motion does not start. So this is called translational equilibrium. If net force acting on an object is equal to 0, so this is named as translational equilibrium. Maybe you can think like this: object is not translating, object stay where it is. If the net force on an object is 0, the object is said to be in translational equilibrium. So then net force, sum of the force acting on the object must be equal to 0. But sometimes we need to think about the component of the forces. Some of the components of the forces must also be equal to 0. Yani, sum of the x component of the force must be equal to 0. And also, sum of the y component of the force also must be equal to 0, which means in this case, yes, sum of the force acting on the objects is equal to 0. So now I'm going to apply this 11th grade part by two examples. There are two forces acting on this object. F1 is acting in positive x direction with 5.3 Newton. F2 is acting in negative x direction with 2.4 Newton. Question is this: calculate the magnitude and direction of the third force. As you see, these two forces are not equal in magnitude. That's why this object is not in equilibrium right now. But by applying a third force, we can keep this object in translational equilibrium. Yani you can make the resultant force acting on the object is equal to 0. Now I'm going to show a method to you. I want you to follow this method. That's why I'm giving such an easy example. So forces are acting along x-axis, is it? Positive x and negative x. That's why you should write that if object is in translational equilibrium, sum of the forces acting along the x-axis must be equal to 0. Two of them is given, but third one we don't know. We will write them right now. So first, when you are writing these forces, if one force is in negative x direction, you are going to write it in this equation negative. For example, 2.4. What is the direction of 2.4?
Yeah, to the negative side.
That's why we are going to write here negative 2.4. What about 5.3?
To the positive side.
That's why you should have positive in the equation. Negative 2.4 plus 5.3. What about third force? We don't know. There must be a third force. We know what, we don't know its magnitude, even we don't know its direction. Now, when we add it, we will get it. So this negative 2.4 plus 5.3 plus F3, if you go on, you will get F3 as negative 2.9 Newton. So this addition is positive. When you get this addition other side, it will be negative 2.9. This negative indicates that F3 must be in negative X direction. So there will be a third force in negative X direction, whose magnitude is 2.9 Newton, and a third force in negative X direction, whose magnitude is 2.9, will make this system to be in equilibrium. Let's draw it now. I will draw with a different color. Yes, F3 must be in that direction. Magnitude of F3 must be how much? 2.9 Newton. Now, this object is in translational equilibrium right now. And now I will do the same thing in vertical. Now, there are again two forces acting on the object. One force is acting upwards, other one is acting downwards, which one of them is 3.8 Newton. The other one is 8.7 Newton. So, of course, because these two forces are not equal in magnitude, there is no equilibrium. But my question, I want you to apply a third force and keep this object in equilibrium. Calculate the magnitude and direction of the third force to keep the object in translational equilibrium. So again, we will use the same rule, but this time forces are in vertical, which is opposite along y-axis. So you will write it about the y components. Sum of the y component of the forces acting on the object must be equal to 0. This time, positive y direction, the forces in positive y direction will be written as positive. Forces in negative y direction will be written as negative. So which one is in positive y direction? 3.8. So you are going to write 3.8 as positive, but 8.7 in which direction? It is in negative y direction. You are going to write 8.7 into equation as negative. 3.8 minus 8.7 plus, what about F3? I don't know, I will find it. Plus F3 is equal to 0. If you go, this result is negative. You take it other side, it will be positive. So result will be F3, positive 4.9 Newton. This positive indicates what?
The direction of the force.
In which direction? Positive
Upward.
y direction, which is upward. Yani positive in here indicates positive y direction, so F3 must be upward in positive y direction. Now let me draw F3 on this object to keep this object in translation equilibrium. So F3 must be acting like this, with a magnitude 4.9 Newton. This is how we find the third force or a fourth force to keep a system in translational equilibrium. This is the method. And normally you should be able to know this from 11th grade. Most probably a little you studied about this, maybe not in this way, but you should learn this way because you are going to use this way in this problem solution of this section. Now I will continue with the 12th grade part. Translational equilibrium. Evet, in fact, translational equilibrium, rotational equilibrium are very similar in sentences. In translational equilibrium, remember, we were looking for net force to be 0. In rotational equilibrium, we will look for a net torque. We will look for net torque. If the net torque acting on a stationary object is 0, pardon, is positive. If net torque is positive, so if net torque is positive, what happens? Positive net torque.
Yeah, the object starts to rotate.
Counterclockwise, değil mi? Positive net torque, counterclockwise. What about negative net torque?
Clockwise.
Clockwise. Yeah, we learned that. Negative net torque, clockwise. What about zero net torque?
It doesn't move.
Yeah. This is what we are talking about. We will talk about this. If net torque acting on a stationary object is 0, rotation does not start, and this is known as rotational equilibrium. Yani if the net torque acting on an object is 0, if net torque on an object is 0, the object is said to be in rotational equilibrium. Object is said to be in rotational equilibrium. And in this section, because initially your object is generally will be in at rest, stationary, so if net torque acting on the stationary object is 0, it will stay in rotational equilibrium. It will stay stationary as well. But condition for rotational equilibrium is what? Net torque acting on the object must be equal to 0, known as rotational equilibrium. Now we have two conditions of equilibrium. One of them is translational equilibrium. For an object to be completely in equilibrium, first, translational equilibrium must be provided, and also rotational equilibrium must be provided. Translational equilibrium, we know sum of the force acting on the object must be equal to 0, and rotational equilibrium must be provided, which means sum of the torque acting on the object must be equal to 0. This is sometimes known as first condition of equilibrium, and rotational equilibrium sometimes known as second condition for equilibrium. If these two conditions are provided, we say that this object is in complete equilibrium. Complete equilibrium. First condition of equilibrium is translational equilibrium. Sum of the force must be equal to 0. And we did this in the 11th grade. Even we did in the beginning of this last lecture. And second condition of equilibrium is known as rotational equilibrium, which is the sum of the torque acting on the object also must be equal to 0. When these two conditions are provided, we say that complete equilibrium. Object is in complete equilibrium if these two conditions are provided.